Welcome. This is Dr. Michio Kaku, Professor of Theoretical Physics at the City College and the Graduate Center of the City University of New York. And this is Exploration. Every week on Exploration, we discuss the fascinating world of science. And today, we're going to answer some of the email letters that I get. Once again, it's impossible for me to answer all the emails that I get. However, many of the emails belong in certain categories, so I'll try to answer the categories of emails that I get. One persistent source of questions I get comes from the concept of ancient aliens. Is it true that ancient aliens visited the planet Earth millions, billions of years ago? Maybe they kidnapped some dinosaurs and took them back to their home planet. Maybe they left evidence of their existence. Maybe the natives of the Earthlings that witnessed these gigantic feats of extraterrestrial science engraved them in their ancient religious ceremonies. Well, we'll say a few things about ancient aliens. And also we'll say a few things about new results from outer space. Four Earth-sized planets have been found orbiting a nearby star that looks very much like our sun, only 12 light years from the planet Earth. And this means that perhaps Earth-like planets are much more plentiful than previously thought. And then we'll say a few things about a recent controversy between two billionaires, Elon Musk, founder of SpaceX and Tesla Motors, and Mark Zuckerberg, founder of Facebook. And they have disagreed on a billion-dollar question, the future of artificial intelligence. Elon Musk says the danger of artificial intelligence is more immediate and more grave than the danger facing us from North Korea. And Mark Zuckerberg says, that's exaggerated. We're talking about AI being a source of wealth, prosperity for the future. And then one set of questions I often get is a question about cancer. Why is cancer so difficult to cure? But, however, there are not one but two new types of therapies that are gradually entering into the marketplace. And so we'll say a few things about two types of immunotherapy and, well, why is it so difficult to cure cancer? And speaking about diseases, we'll also say a few things about amyotrophic lateral sclerosis, the disease that afflicts my colleague, Stephen Hawking, and a new breakthrough has been made in terms of isolating the cause of ALS. Well, unfortunately, there's no cure for ALS, but perhaps we'll have a clue as to how one day a cure might be found. And then we'll say a few things about the eclipse. Maybe some of you people out there saw the eclipse, but it also indicates something about the birth of science. And the question is often raised, who discovered the formula that allows us to predict the coming of the next eclipse? That's a heated debate among historians. However, there is a device found in 1900 from a shipwreck, which is now revealed as an eclipse calculator. That's right. We now know that a device 2,000 years old was actually a mechanical eclipse calculator. And then the next question is, who built it? Who could have possibly had the smarts to create a mechanical computer, in some sense, that calculates eclipses 2,000 years ago? Well, let's just jump right into some of the emails that I get. One persistent source of emails I get concerns ancient aliens. You've probably seen some of these shows on TV. In fact, I've been on some of them myself, where you have interviews with archaeologists and people that study drawings made by ancients. And by golly, in some of these drawings, the headdresses of these ancient religious types look very much like the headdresses coming from NASA. That is, it looks very much like they're wearing a space helmet with oxygen tanks, maybe even jetpacks. And they seem to be riding some kind of instrument, perhaps a shuttlecraft that takes them to the mother ship. Well, the question is that really a valid source of scientific speculation? Well, yeah, it is speculation, and in principle, you cannot rule it out. You cannot rule out the fact that, well, perhaps we were visited by ancient civilizations that were far superior to us in their in their space technology. However, science wants to go beyond that. Science wants to go beyond simply the drawings and the imagery. They want hard evidence. You see, science is based on things that are testable, reproducible, and falsifiable. And these ancient cave drawings and these ancient religious monuments fail on all three. For example, these are hard to falsify. Can you create an experiment that would allow you to disprove the fact that these are artifacts coming from an alien visitation? And the answer is no. It's like trying to disprove the existence of unicorns. You can always say that someplace on the planet Earth, in a hidden cave that no one has ever visited, there's a unicorn. And that's the problem of disproving a negative. Many times, you can't do it. You just can't do it because maybe someplace out there is a unicorn hiding someplace where no human has ever ventured. And therefore, these questions are actually outside the boundaries of science. For example, I was once at a cocktail party, and someone there claimed to be the reincarnation of Cleopatra. Well, yeah, it's possible. Who knows for sure? But when you ask simple questions about Cleopatra, all the answers come out incorrect. But then the response to that was, the questions are all incorrect. The history books are incorrect. How do I know? Because I am the reincarnation of Cleopatra. So how do you disprove something like that? And for that matter, how do you test? There's no biological test that you can make that would falsify or prove that this person was in fact the reincarnation of Cleopatra. So I'm not saying that ancient aliens haven't visited the planet Earth. There's a strong likelihood that maybe it actually has happened in the past. But we need hard evidence. Now, the skeptics that I've also interviewed say to me that if there was a base, a rocket base for aliens that came to the planet Earth, there should be garbage. There should be wires. There should be leftover Coke bottles or whatever they drank. There should be some evidence of this previous visitation indicating advanced technology. And unfortunately, we don't see any at all. We don't see alien pliers, alien wires, alien radios, chips, or anything that involves very advanced technology. And also, maybe these drawings of people with elaborate headdresses, maybe these headdresses are not helmets at all. Maybe they're just that. They're just headdresses. So, in other words, sometimes the simplest answer may be the correct one. Now, personally, I think that, yes, you cannot rule it out. The possibility of ancient visitations, if you saw the movie 2001, is based on the idea that perhaps we were visited millions of years ago by a civilization that created robots. Robots that were self-replicating, robots that landed on the planet Earth and surveyed the situation with regards to intelligent creatures and actually accelerated the evolution of Homo sapiens. Can you rule that out? And the answer is no, especially because these robots came from the moon. And in fact, that's probably the most likely place for ancient visitations. The moon is sterile, has no erosion, no rust, no rains to worry about, no flooding. It's an ideal place to put a probe. And so a civilization very advanced would not send Captain Kirk on a very expensive enterprise to explore the galaxy. There's simply too many stars. No, they would send self-replicating robots like a virus that land on a moon, create thousands of copies of themselves that then go to thousands of more moons, each one creating thousands of more probes. Starting with one probe, you get 1,000, then 1,000,000, then 1,000,000,000, then 1,000,000,000,000, then 1,000,000,000,000. And in just 5 generations, you're going to have an uncountable number of space probes, robots, going out throughout the galaxy. And that's the most mathematically likely way that an advanced civilization would explore the universe. And so some friends of mine have actually stated, these are physicists, that the next time we go back to the moon, or even looking at previous records of our visitations of the moon, we should look for alien energy signatures. indicating the presence of an advanced device, perhaps in the dust of the surface of the moon, indicating that they're in communication with the mother planet. Seriously, this is not just idle speculation, but it turns out that Professor Paul Davies at the University of Arizona in Wisconsin has actively proposed that we should either go back to the moon with new eyes or with the next generation of space probes to the moon, actively look for evidence of a probe left over from an advanced civilization. That would really be a game changer. And speaking about outer space, astronomers were elated to find that the nearest sun-like star has not one, not two, but four, count them, four Earth-like planets going around them. Now, even children know that the closest star to our sun is Alpha Centauri. The problem is that it's a red dwarf, a very tiny star, Proxima Centauri, of the Alpha Centauri system. And it means that probably a planet circulating that red dwarf is not going to be able to sustain life. You see, red dwarf stars are not only tiny, but they're also quite active. They emit lots of solar flares. And any planet next to a red dwarf might have their life forms wiped out by these solar flares and solar storms. That's why we want to find a sun-like star, very similar to our yellow sun, and that's what scientists did. It turns out that the closest yellow star that resembles our sun is called Tau Ceti. It is 12 light years away, and when scientists scanned this star system, bingo, they found four Earth-like planets going around Tau Ceti. And that means that perhaps these planets could sustain an atmosphere. Perhaps they could have liquid water in their surface, that is, oceans. And who knows, perhaps even microbial life. We don't know for sure. Perhaps it means that Earth-like planets going around sun-like stars is perhaps much more common than we previously believed. And just remember that because of the Kepler satellite, we have found thousands of planets orbiting other stars in outer space, a handful of which look very close to the planet Earth. And also, on the medical front, there are not one but two new therapies in the fight against cancer. Well, one question I often get is, why did the war on cancer end in a failure? President Nixon, with much fanfare, announced a war on cancer. Well, some of the cynics have said that cancer won. We don't have a cure for cancer, even though decades ago, President Richard Nixon vowed a war on cancer. Well, what happened? First of all, you realize that back then, there was no Human Genome Project. We were blind. You see, we now realize, because of the Human Genome Project and other developments, we now realize that cancer is really a disease of the genes. When 4 major genes are damaged, approximately 4, that's enough to send the normal cell into this aberration called a cancer cell, whereby it simply becomes immortal. These ordinary cells that are mutated simply reproduce forever until they form a tumor, and then the tumor eventually kills you. So that's why we couldn't win the war on cancer. We didn't have a roadmap. Think of it. If you're a general and you want to fight against the enemy and you have no roadmaps whatsoever, what are you going to do? You're going to get lost. And so for the last 50 years or so, we've been using surgery, chemotherapy, and radiation. We want to cut the cancer, poison the cancer, and zap the cancer. And that's the way it's been for the last 50 years. And these 3 therapies have horrible consequences. Your hair falls out, huge chunks of your flesh are cut out, you're constantly in a state of nausea, the enormous discomfiture of chemotherapy. Well, today we still cannot cure cancer totally, but at least we have 2 new ways of attacking cancer using immunotherapy. The first way is to extract immune cells from your own body, grow them and strengthen them outside the body, and then inject them back in the body. That is one very promising way in which to attack cancer. The other way is even more experimental and perhaps even more promising than that. and that is remove the T cells of your immune system, and once they're outside the human body, grow them and genetically modify them. Genetically modify them so they can recognize cancer, and then re-inject them back into the human body. You see, believe it or not, you have cancer all the time. In other words, cancer cells grow naturally in the human body because of mutations in these 4 major genes that I mentioned. But you see, for the most part, your cells can identify these aberrant cells and kill them. So we get cancer all the time in some sense, but we have a mechanism in our immune system. But you see, over time, some of these cancer cells learn to develop a protein coat that makes them invisible to your T cells. And as a consequence, you then come down with cancer. These cells cannot be attacked by the immune system. They simply grow and grow and grow, create a tumor, which eventually kills you. This is where gene therapy comes in. We can now extract these cells from the human body, modify the genome so that they can, in fact, recognize the protein coat around a cancer cell, re-inject these modified T cells back into the body, and bingo, it seems to work. In fact, some of the individuals that have been tested with, they apparently have been cured for the most part, no trace of cancer left. So, of course, these are still in their infancy, these various immunotherapies that I talked about. Some of them have after effects that have to be worried about. We still don't know the exact percent of efficiency of these systems. However, the very fact that we can talk about this, I think, is enormous. It means that for the first time, we have in our arsenal a way of directly attacking the cancer cells by strengthening the immune system of the human body. I should also point out that some people believe that perhaps we'll never have a single cure for cancer at all, but cancer may eventually be like the common cold. Think of the common cold. We know that it's caused by roughly 300 different types of rhinoviruses. So why don't we invent a cure, a vaccine, that protects us against all 300 rhinoviruses? Well, it's cost. It would take up too much time, too many resources to develop a vaccine for all 300 or so of the rhinoviruses. Plus, they mutate, creating new varieties. And so we just learn to live with it because a cold, for the most part, doesn't kill that many people. Eventually, the same thing may happen with cancer. This means that in the future, we will, in fact, cure some cancers outright. But it does mean that we may simply live with other cancers, but neutralize them to the point where they become harmless. That is, they don't kill anyone. In other words, just like we live with the common cold, in the future, we may learn to live with cancer because it's simply not the lethal disease that we're accustomed to dealing with. Also, speaking about the medical front, I sometimes get questions about my colleague, Stephen Hawking. He has ALS, amyotrophic lateral sclerosis, which destroys your nervous system, but basically leaves your brain intact. So you are there to witness the slow degeneration of your own body while your brain is fully functional. ALS is a horrible disease. It kills you within a few years. However, my colleague Stephen Hawking apparently has a new variety of ALS so that he is still alive, kicking, and participating in scientific debates, believe it or not. However, there is no cure for ALS, but the good news is that a team of scientists have identified a gene, TIA1, that when mutated, seems to be involved with creating ALS and damaging the nervous system. They found this gene, the gene for TIA1, by analyzing family history. Yes, it turns out that some families are stricken with ALS. And then you analyze the genes from these families, and you ask yourself a simple question. What common gene links all these individuals with ALS? And that's how they zeroed in on this one gene, TIA1, which seems to be involved with the creation of these ALS-infected families. Now, the people who did the study are very careful to say that they have no cure. At the present time, there's no cure for ALS. However, the first step toward a cure is to identify what's causing it. And that's what these scientists were able to do. For the first time in history, they're able to take one variety of ALS and show that it's involved with the mutation of one protein. And in the future, perhaps people will be able to manufacture the correct protein and use that as a form of therapy. But that, of course, is still in the future. Also, some of you may have seen the eclipse, a total eclipse of the sun. And many people were startled to realize that, yes, science can not only predict when these eclipses are coming, but we also know exactly what shape, what form, what type of eclipse is coming along, down to the second. And then you ask yourself a simple question. When did we first figure that out? I mean, the ancients, since time immemorial, have been fascinated by the heavens, but afraid. Afraid because the events in the cosmos seem so unpredictable, like meteors and comets and eclipses. And so, when was science able to predict the first eclipse? Well, we don't know for sure. It probably goes back 2,000 years or so, back to the ancient Greeks and the ancient mathematicians. However, there was a new discovery made several years ago which may force us to rewrite the history. It turns out that in the year 1900, there was a shipwreck off the coast of Greece. And in the shipwreck, scientists found a mechanical device of some sort. It's amazing because scientists did not believe that 2,000 years ago, the ancients were even capable of creating a mechanical device. Much to the surprise, over the decades, as science began to develop, we began to peer inside the workings of this device, and we were shocked. We found out that it was basically a computer, not an electronic computer, because they didn't have electronics in those days, but a mechanical computer with gears. Gears that seemed to point out the motion of the planets. Well, that's not so hard because, of course, many astronomers have been able to simply look at the planet Venus and basically predict the motion of the planet, giving us previous history. But no, this device went even further. It predicted when we would have the next lunar and solar eclipse. Now that is much more difficult than simply predicting the motion of Venus across the heavens. That requires knowing the plane of the Earth-Moon system, the plane of the Earth-Sun system, and so many other parameters that we just didn't think the ancients were capable of doing it. But there it was. In fact, every year, as scientists begin to decode more and more of these ancient inscriptions and ancient gears, we're beginning to realize that, yeah, the ancients were, well, not as dumb as we thought they were. They were able to calculate from the eclipse the size of the Earth-Moon system. Think about that. Being able to calculate the size of the Earth, the size of the Earth-Moon system, using the power of trigonometry, the eclipse, the position of the sun, and the position of the moon. The ancients were able to figure it all out. Amazing. And this mechanical device actually gives you proof. Proof, not just hearsay, but proof that, yes, the ancients did, in fact, have a device to predict the motion of the planets, the star, the sun, the moon, and the coming of the future eclipses. Amazing. Well, looking at my mail, another listener says the following. After all this hoopla concerning the eclipse, was it all for nothing in terms of science? I mean, we have space probes. We don't need eclipses in order to analyze the sun, right? Well, yes and no. It turns out that this eclipse was the most heavily studied eclipse in human history. But there's also a reason for that, because there are things that we simply don't know and understand about the sun, believe it or not. For example, the surface of the sun is roughly 10,000 degrees, but the outer atmosphere of the sun, the corona, temperatures can reach over 1,000,000 degrees, and that violates common sense. Common sense says that the farther you are from the surface of the sun, the cooler it should get, but no, it's the opposite. The hotter you get, the further you go away from the sun. And why is that? Well, we don't really know. It has something to do with the magnetic storms on the surface of the sun, which convey energy. And these solar storms, in turn, are very interesting because they're the basis of coronal mass discharges, gigantic solar flares that can reach the planet Earth. In fact, there was one solar flare years ago that hit Quebec and knocked out power in that area, not to mention that our astronauts are told to seek cover in the space station whenever a gigantic coronal discharge is passing by. Luckily, they missed the Earth. So think of the sunspots of the sun being like rifles. You shoot these rifle bullets into outer space, and for the most part, they miss the Earth. But one day we will have a direct hit. In fact, a few years ago, we almost had a direct hit. It turns out that 150 years ago, in 1859, there was a direct hit with a coronal mass discharge. Luckily, back then, we only had telegraph wires, which were burnt out as a consequence of that event. But we physicists can work backwards. Knowing the fact that the coronal discharge of 1859 was sufficient to disrupt telegraph wires, we can calculate the energy density in the atmosphere due to that flare. And then we were to say, if it happens again in the space age, what would happen? Well, all hell would break loose. Satellites would get burnt out. The internet would go down. Television, radio would be disrupted. Power plants on the Earth would get short-circuited. Food riots would eventually spread because people would have no electricity for their refrigerator. Supermarkets would very soon empty out. And replacements and the cavalry are not coming because they too would be disrupted. Now, we physicists estimated that property damage could be on the order of $2 trillion. That's trillion with a T. We went to Congress and asked for a few $1 million to begin the process of redundancies and creating reinforcements for our power stations and satellites. And all we got from Congress was giggles, the giggle factor. What? An attack from the sun, from outer space? Tax dollars to protect us from the sun? Give me a break. Well, unfortunately, we got nowhere. So who knows? One day it could happen. Food riots. Civilization itself being thrown back 100 years into the past. Well, that concludes the first part of exploration. In the second part of exploration, we'll continue our discussion about outer space. And the question is, what about women astronomers that helped to pioneer astronomy back near the turn of the century? We're going to interview George Johnson of the New York Times talking about the life of Henrietta Leavitt, a pioneering woman astronomer whose basic discoveries allowed us to measure the distances in the heavens, to create a yardstick by which we can measure the cosmos. Welcome. Once again, this is Dr. Michio Kaku, Professor of Theoretical Physics at the City College and the Graduate Center of the City University of New York, and this is the second half of Exploration. In the first half of Exploration, we talked about, well, things like health, cancer, and the universe. And we mentioned the history of eclipses. But then the next question is, how do we measure the distance to the moon and the distance to the sun and the planets? Well, the Greeks did a very good job using the eclipse. They were able to calculate using geometry the distance from the Earth to the moon. And this is an amazing feat that by using the eclipse, they were able to calculate some of the dimensions of the universe. But then the question is, how far are the stars, the faraway stars? Well, for that, you need what is called a standard candle. In other words, if you look at the headlights of a car could be very far away, but its headlights could be very bright. Or the car could be very close to you, but the headlights are very dim. In both situations, the resulting light could look very similar. And so obviously what you need is one more variable. That is, you need to know the intensity of the headlight. Ideally, you want a standard candle. That is, a candle that is the same throughout the entire universe. Given that, then you can calculate the distance to the headlights, and for that matter, the distance to the stars. And so that was one of the key discoveries made by Henrietta Leavitt, that she was able to get a yardstick by which you could calculate the distance to the heavens and thereby open up the world of astronomy to rigorous scientific debate. Sadly, her work was not recognized. It was lost in the rewriting of history, and as a consequence, she never fully got the credit for a discovery of how do you measure the universe. Now, Henrietta Leavitt made her discovery by painstakingly analyzing something called the Cepheid variables. They are variable stars. They seem to pulsate in light intensity. However, what is very interesting about the Cepheid variables is that no matter how far they are away, they seem to be the same. That is, we now have a standard candle by which we can measure the dimensions of the universe. She found that the Cepheid variables are, in fact, the standard candles anywhere in the universe, and you can calibrate them. You know exactly how bright they are using a formula that she came up with. However, she never got credit for it. So today, we can measure the scale of the universe using the result of Henrietta Leavitt, who in her own lifetime, and many lifetimes afterwards, never got any credit for her great discovery. We also have the sad story of Jocelyn Bell, a woman graduate student who discovered the pulsar, but it was her thesis advisor who won the Nobel Prize in Physics for the discovery of the pulsar. And we also have the sad story of Vera Rubin. Back in the 1960s, she was one of the first people to point to the fact that the universe seems to be full of something called dark matter, but her result was ignored, and only recently has the theory of dark matter been given experimental verification because of all the males who have now jumped into the field. So our special guest today is George Johnson. He's a writer for the New York Times Science section, also author of many books, including Fire in the Mind, Strange Beauty, and his latest book is called Miss Leavitt's Stars, the untold story of the woman who discovered how to measure the universe. And it's one of the scandals of science that Henrietta Leavitt never got the credit for measuring the universe. The first question for you is, how did you first get interested in science as a youth?
I think it must have been a combination of the All About books, these great children's books about different scientific subjects, and then there was the whole space program, which was just getting off to a start, and I would see these wonderful pictures in Life magazine and the Saturday Evening Post, and sometime around the second grade, I wrote my first book, which was called The Solar System.
Oh, really?
It was made of, from Big Chief tablet paper and my father's shirt cardboards and crayons, with one page for each planet. But, not a very penetrating treatment, I don't think. Nothing like Davis Sobel's new book.
Now, you also mentioned that you read science fiction as a child.
Yes, later on I did. Junior high school, I really got interested in reading Isaac Asimov and Ray Bradbury and Robert Heinlein, and that was very inspiring. I mean, there's a one Heinlein story that I mentioned in my introduction about the telepathic twins that can.
Yeah, I read that book too as a kid.
Oh, did you?
Yes.
Oh, well, that just really the thing that really moved me in that was the idea of them landing on this planet in a distant star system and looking back and seeing the Earth as a tiny little star that's part of a suddenly unfamiliar sky. It's all distorted by this different point of view.
Mm-hmm. Yeah, when I read that science fiction story as a kid, I said that, gee, two twins communicating telepathically faster than the speed of light? No, give me a break.
You were way ahead of me. I bought that hook, line, and sinker, although I didn't know it was fiction.
Now, why did you decide to write a book about Henrietta Leavitt, who, for the most part, is this tiny little footnote in most astronomy books, but most astronomy books wouldn't be written without her work?
Yeah. partly out of a sense of frustration, because I keep seeing these little footnotes or these kind of two-sentence glancing mentions of her work, and I started to get this picture in my mind of this woman around the turn of the century, kind of little post-Victorian time, sitting up in some dark room in the Harvard Observatory in Cambridge and poring over these star charts. And that image kind of fixed itself in my mind, and I thought I would start a book about measuring the universe with Henrietta Leavitt, just kind of to get into the book. But then I just really became very curious about who this person was and what, if anything, we knew about her, and was lucky enough to find some documents with a good researcher in the Harvard archives that helped flesh out her story a little.
Okay, well, let's now set the stage for exactly why her discoveries are so important. In ancient times, of course, ancient peoples would look up at the night sky, look at the stars, and wonder, how far are they? You can't throw rocks to hit the stars. You can't jump. Even the highest mountaintop, you can't reach the stars. So how did astronomers first begin to estimate the distance to the stars?
Yes, and they were able to estimate distances to things on Earth using triangulation. And, we do the same thing with modern surveying, where you look at something from two different vantage points and see that it shifts slightly against the more distant backdrop, and you can use trigonometry to figure out how far it is. And Hipparchus, in ancient Greek times, did that with the moon and got a pretty good estimate of the distance. But the stars are so far away, even the closest star, that you could measure from two different parts of the Earth, and you wouldn't see any shift of the position, so you can't triangulate. So it was a big problem with the stars tiny and close by, or enormous and very distant.
Now, this process is called parallax, and it's also the reason why we have two eyeballs.
Yeah.
So explain to us why we have two eyes rather than one eye, and if you injure one eye, it's quite difficult to judge distances.
Yes. If you think about your eyes as forming the ends of the base of a triangle, you're essentially triangulating unconsciously on things as you look outside. Like right now, I'm looking out my office window at this old church across the street, and as I walk around through the window, the church, seems to move against the backdrop, and my brain is presumably doing some unconscious computations and giving me a sense of how far away that is. So if we were born with one eye, we would always be running into things because we didn't know how far away they were.
And that's also how 3D glasses work, right? Your left eye sees red, your right eye, the other eye sees blue,
right.
And your brain puts the red and the blue together to create a three-dimensional image.
Yes, right. Or those old stereopticons where you have the two postcard images that are slightly different, one for each eye, and it gives you a 3D effect.
Mm-hmm. Okay, so the radius of the Earth's orbit around the sun is about 93 million miles or so.
Right.
And so if you take a picture of the night sky in summertime and a picture of the night sky in wintertime, you've actually moved the telescope over almost 200 million miles, right?
Yes. So you can imagine it's like having an eye on each side of the solar system, and from seeing how some of the stars, the very closest ones, shift a little between every 6 months. That gave astronomers a way to triangulate the distance to the very, very nearest stars, those just a few light years away. But most of the stars by far are so distant that you don't see any parallactic shift at all from season to season.
Now, children often say, gee, Daddy, how come the moon is following me? Everywhere I move, the moon is following me. But that's because the moon is so far away, it has no parallax, and it gives you the optical illusion that it's always above your shoulder, right?
Ah, yeah, I'd never actually thought about why that was, but sure, of course.
Now, also, a light beam from the Earth to the Sun takes about 8 minutes. Mm-hmm. So the diameter of the Earth's orbit is about 16 minutes by light. But you just mentioned that the nearby stars are tens of light years away that are familiar to us every night. Mm-hmm. And so the parallax must be very small to the faraway stars, right?
Yes, it was just a fraction of a second of a minute of a degree. So it was a very, very delicate measurement, and something that wasn't really possible until I think it was the 19th century, when they really had equipment good enough to make measurements that finely.
Mm-hmm. Now, usually when we judge distances, we use what is called a standard candle. If I have a candle that is the same everywhere in a room, and I move the candle anywhere in the room, I can judge distances because the fainter the candle, the farther it is away.
Right.
It's the same candle. But stars are not standard candles, right?
Yeah, we had no way of knowing how bright they were inherently. So, again, it's the question of, is it very bright and really close to us? I mean, very bright and really distant, or is it very dim and really close to us, or somewhere in between? But yeah, without actually going out there in a spaceship and measuring it up close, it was a big mystery of how we'd know how bright they were, so we could calculate their distance.
Mm-hmm. Okay, now let's go to the 1920s, where when astronomers had a pretty firm idea that the Milky Way galaxy, which we see every night, this swath of light cutting across the night sky, that the Milky Way galaxy was in some sense the entire universe.
Yes.
Could you explain to us how we viewed the universe in the 1920s?
Yes, that was one of the things that I really found most astonishing, and that drew me into wanting to write a book about measuring the universe, was to realize that as recently as 1920, it was a matter of scholarly scientific debate whether the Milky Way was the whole universe or not. And if that were true, then something like Andromeda, which we now know to be a neighboring galaxy, would be instead just a very small little smudge, a little bit of stellar dust or something very, very close into Earth. And that's certainly what Harlow Shapley, one of the great astronomers of the 20th century, thought.
And in fact, wasn't there a great debate that you mentioned in your book concerning the structure of the universe and how far the stars really are?
Yes, in Washington, D.C., at the National Academy of Sciences. And Shapley took the position that the Milky Way is the whole universe and that there aren't any other galaxies. And Heber Curtis, another astronomer, took the opposing view that actually the Milky Way was just one of many, many of what Immanuel Kant had called island universes, or that there are many galaxies, and Andromeda was being one of them, and the Magellanic Clouds being a smaller satellite galaxy. So it was a very, very heated debate, and each man really left Washington convinced that he'd won.
So how big was the universe to Harold Shapley? In the early 1920s, he must have had an estimate as to how big the Milky Way galaxy was, and that was the universe. So how big was the universe to him?
Well, let's see. I can't really immediately recall the number from Shapley's calculations, but he used the standard candles that Henrietta Leavitt discovered to kind of measure out the Milky Way, and but it was just, obviously vastly smaller than the universe that we know about today.
Okay, well, now let's get into Henrietta Leavitt's work itself.
Yeah.
Tell us a little bit about where she was born, where she grew up, and how did she wind up as an astronomer at Radcliffe?
Yeah, it was a very interesting trajectory. She was the daughter of a Congregationalist minister, very, very Puritan kind of upbringing in Lancaster, Pennsylvania. And at some point her family moved to Cambridge, Massachusetts, where her father had a church, and later out to the Midwest, to first Ohio and then to Wisconsin, Beloit, Wisconsin, and she followed the family there. And the family valued education, and they encouraged her to go to school, and she was in Beloit College in Wisconsin at first, and then later transferred to Radcliffe University back in Cambridge, Massachusetts, partly because she had relatives there. And during school, she had what was really just a general liberal arts education. She had some science classes, but mostly humanities. Toward the end of her time there, before she graduated, she took some astronomy classes that were taught by astronomers who just walked across the street from the Harvard University Observatory, and that's when she got hooked. And she took a volunteer position at the observatory right after school, right out of school, and this led into her job as what they called a computer, someone who was hired to do calculations.
Now, even today, grad students have to support themselves either by part-time jobs or scholarships or what have you. You mentioned in your book that she came from probably an upper-middle-class background, so she probably didn't have to worry about a job, right?
I think she probably, I was never able to confirm that, but it seems clear that she must have been of somewhat independent means, because there are these letters in which she talks about going off on cruises to Europe and things, and she was being paid 25 cents an hour, which, if you put it into an inflation calculator, comes out to be about $5 in today's terms. So, basically what you'd make working at McDonald's.
Okay. So I understand that back then, of course, they didn't have calculators, and astronomers relied upon teams of women to do their calculation for them. Is that right?
Yeah, they tended to be women, and it was considered a good job to get at the time. It paid better than working in the cotton mills, and of course, for someone like Henrietta Leavitt, it was a somewhat intellectual occupation. She seemed to enjoy it, and a computer at the Harvard observatories wasn't only adding up columns of numbers and doing calculations, but also studying these photographic plates of the sky that had been taken at the Harvard Observatory down in Peru. So it was pretty interesting work, I guess, for someone who was interested in astronomy, but then also very, very tedious, very, very painstaking work. And there was a certain sense that it was women's work, and the men would make the discoveries and talk about what the stars meant and interpret the data, but the women were there to gather it.
And precisely what did she do to change the course of astronomy?
The director of the observatory, Edward Pickering, he quickly realized that she was, very, very good at this, and even very overqualified. At one point, he gave her a raise to 30 cents an hour. And he assigned her a project of looking for variable stars in this haze of light called the Magellanic Clouds. This had been photographed by the Harvard Observatory in Peru, because you can only see the clouds in the southern hemisphere. They look somewhat like the Milky Way, except round. So Leavitt was looking at these plates and asked to look for stars that varied in brightness from week to week or month to month, and sometimes even from day to day. And she'd do this by comparing a plate taken, say, in January with one taken in February of the same part of the sky, and then would look for stars that had varied in brightness. So she was doing this, and she discovered just a very large number of variable stars within the Magellanic Clouds. So she was curious about how, what their periods of pulsation were, so she made a list, and at some point she noticed that there was a correlation, so that the dimmer a star was in the Magellanic Clouds, the dimmer a variable star was in the Magellanic Clouds, the more rapidly it blinked, and vice versa. And she drew a little graph and showed that there was a definite relationship between the star's rhythm of pulsation and its dimness or brightness.
And how could that be used to then establish a standard candle that could be used throughout the universe?
Well, essentially, since all these stars were in the Magellanic Clouds, she knew they were roughly the same distance from Earth. So it essentially meant that you could measure the rhythm of the pulsation, and from that you could derive the inherent brightness. It would sort of be like if an international commission had decreed that 50-watt light bulbs blink at a certain rhythm, and that 100-watt light bulbs blink at a different rhythm, and that there was an exact relationship between the dimness and brightness. And then if you looked out your window out onto the town, you could tell by how fast a bulb was blinking how bright it was. And once you knew how bright it really was, you could calculate how far away it was using the inverse square law.
Okay, so what astronomers did was they looked at a variable star, calculated how fast it was blinking. That would then tell you how dim or bright it was. And since these are standard candles, that would tell you the distance to the star.
Exactly.
Then.
And they very quickly found that there were variable stars within the Milky Way, and they were able to use this to get, kind of a sense of, they had to calibrate the scale, in other words, because they could say that, well, here's a variable star blinking, at this rate, so it must be so many, times further away than the second star that's blinking at another rate, but it was all relative distances at that point.
So she was aware, therefore, of the importance of her discovery, right?
Yes, it was clear, and that's one thing that has kind of been controversial, at least from some things you'd read. You'd almost think that she had just gathered the data and that Edward Pickering or someone had figured out the relationship. But if you really look closely at her paper, it's just obvious that she knew exactly what she'd found and why it was important.
So she published her results, so you could then infer from the publication exactly what she knew and what she didn't know, right?
Yes, right. And, there's always a question of, her being an assistant in a computer and working for Pickering. There's a question of how much input he had into the papers, but it was, right there with her name on it, and that's what counts.
Uh-huh. So in some reports I've seen, they sort of treat her as just a computer that just punches out the numbers, but she didn't know what the numbers meant. But you're saying that she actually did know that she had discovered a standard candle. Yeah,
there's one part. Her papers are very, she was a very reserved, quiet woman, and her papers reflect that. And toward the end of one of them, she basically mentions that this would, be a means of distance measurement. And she says it in such a way that it just comes out very clearly, like aha, you can see the light bulb going off in her head.
So wasn't this heralded as a big discovery?
Well, kind of. You'd think. Within astronomy, people quickly realized it was important, and an astronomer named Ejnar Hertzsprung used Henrietta Leavitt stars to measure some distances within the Milky Way, and first started calibrating the yardstick. And then Harlow Shapley, who went on to become the head of Harvard Observatory, used Leavitt standard candles to really map out the Milky Way and just show how great it was. But the real big breakthrough came when another astronomer, Edwin Hubble, found some of these Cepheid variables, they're called, Leavitt stars in the Andromeda Nebula. And once he knew that he had these standard candles there, he could measure how far Andromeda was and show that it was not, as Shapley believed, this little smudge close by, but that it was indeed a huge galaxy.
Now, so what Edwin Hubble did was he took Henrietta Leavitt's result to show that the universe was a hell of a lot bigger than originally thought, right?
Well, yeah, sure, because once you show that there's one galaxy, before long it was just one after another, and many of them were measured using Henrietta Leavitt's yardstick. And once they knew roughly how far Andromeda and some of the nearer galaxies were, they could use the whole galaxy as a standard candle. So if you made the not completely justified assumption that all galaxies are roughly the same size, you could see a galaxy that was smaller and dimmer than Andromeda and rough out at least some sense of how far away it might be. And then more precise standard candles involving whole galaxies have been developed. But really, it's all the whole yardstick comes down at its very base to these Cepheid variables that Leavitt discovered.
So, in other words, during Harold Shapley's time, the universe was perhaps 50, 100,000 light years across.
Yeah, that sounds right.
And here comes Hubble saying the Andromeda galaxy is millions of light years across, and that the universe could be billions of light years across. I mean, this is a huge, huge discovery, right?
Yeah. No, I mean, it's really, as far as breakthroughs in the history of astronomy, going from thinking that the Milky Way was the whole universe and I think the number it's coming back to me was 300,000 light years as Shapley had measured it across for the Milky Way, and and it was just a little bigger than that in his mind, the whole universe. And then Hubble finds that Andromeda is, according to his first measurement, 1 million light years from the Milky Way, and later with some revisions it turned out to be 2 million light years away, and that was just the beginning.
So did people recognize the importance of Henrietta Leavitt's work, or was it simply a footnote even back then?
Yeah, totally a footnote. And the people who got the glory were Hubble and his successors. And people would mention Leavitt appreciatively, and but basically it was a footnote or a glancing mention. And some people have suggested that if her story had really gotten the airing it deserved, that maybe now we'd have a Leavitt space telescope as well as a Hubble space telescope. Or she did get a crater on the moon named after her.
Now, I understand she also passed away fairly early and wasn't alive really to see the enormous application of her discovery. Is that right?
Very, very sad. She clear what it was until toward the very end. She was hospitalized with stomach problems, and it turned out she had stomach cancer.
Well, unfortunately, our time is up. Once again, this is Dr. Michio Kaku, Professor of Theoretical Physics at the City College and the Graduate Center of the City University of New York. And this is Exploration. Our special guest today was George Johnson of the New York Times, talking about pioneering women astronomer Henrietta Leavitt. Good day.